Miss Ahshead in the Period 7 Physics class presents Phun with Physics! Mr. Newton's First Law of Motion by Kristen Ryan. Is in its state of rest, of motion in a straight line at a constant speed, unless it is compelled to change that state by forces exerted upon it. Let's watch.
Tend to stay at rest.
Can we see that again?
An object will stay at rest unless a force acts upon it.
Alright, do a couple.
Motion tends to stay at motion unless a force is acted upon it. There was friction. If there was no friction, an object would tend to stay in motion at a straight line in a constant speed. So friction. An object would move in a straight line indefinitely at a constant speed. This is an example.
Alright.
Motion. Tend to stay in motion.
Mr. Newton's Second Law by Phun and help. With help. Who did her Physics is Fun project on Newton's Second Law? Tracy?
Thank you, Chris. Let's see. Newton was the first to realize the acceleration that we produce when we move something depends not only on how hard we push or pull, but on the mass as well. So we came up with Newton's second law, and that is, the acceleration produced by a net force on a body is directly proportional to the magnitude of the net force, in the same direction as the net force, and inversely proportional to the mass of the body. And in shorter terms, it's F equals ma, which is force equals mass times acceleration. And that's what Newton's second law is. And good. Okay, this is my assistant, Cindy Odom, and she will be helping me to demonstrate Newton's second law. Say something. I will be demonstrating that acceleration equals force over mass. She will demonstrate that acceleration will vary with constant forces of different masses. She will first demonstrate the light ball and how fast it moves. Whee! I'm not going to talk this time, I'll talk next time. Maybe I should go first. We'll demonstrate the heavier ball, the next heavy size one. Then that was the tennis ball. Okay. That's harder to push because it's heavier. Heaviest mass of all, the kickball. Hard to push. Okay.
Average speed. speed presented to you by David Mack.
Here in our left corner, we have the Physics Country Store, which services the city Newton's Apartments, or which is in the city of Acceleration City. Alright. We have the Distance Railroad that commutes to and from the town. And if you want to go fishing, you can always go fishing on Refraction Lake. Kinetic Lane will take you there the nearest way. And if you want to go back to the apartments, you can always take Adset Boulevard. Oh, and we have the potential energy power plant, giving you the power for the daily races that you see here. Our physics problem is involving average speed. The car will go around the track 2 times with a time being measured. The car will then proceed around the track, how many times did you shoot? 6 more times with a time being measured. Taking the distances, dividing by the sum of the times will give you the average speed of the total car around the whole track during the whole time of the trip. Are there any questions?
No.
Okay. Let us proceed using a regular watch to record seconds.
Oh, brother.
Our friend, the timekeeper, Mr. Stubbelow, will record this time. I will provide the power to the car. The car's name, by the way, is velocity number 1, speed number 1. Okay. So the car will travel around 2 times, and Stubb will give you a time reading. And he will record it down on the piece of paper. Okay, so you write it down.
Okay.
2 times around the track.
Go. Five and a half.
Okay, 5.5 seconds. Now the car will continue to travel around the same track, same distance, for 6 times.
All right. Now keep a track.
Yep.
You say stop when it's after completion. On your mark. Get set. Go. Whoa!
Minus the
Close out quarter number 2. Don't we need the tow truck? All right, we're starting over, right?
You want to start over, or you want to add that in there? Doesn't matter.
All right, we'll add that in.
Okay. One more.
26 seconds.
All right. I have calculated the measure of the track, converted it from inches, because this is American track, into centimeters. It adds up to 259.08 centimeters. Now, by using this formula,
Let me see that formula, Dave Mack.
all right, using this formula, average speed, taking total distance the car went, okay, Stubb will take 259.08 centimeters. Sorry. There's one.
And
Plus 259.08 centimeters.
plus what?
259.08 again,
Oh.
or times 2. Divided by 5.5 seconds plus 26 seconds will equal
120.21.
120.21 centimeters per second the car travels while going around the track.
I don't think so.
Why?
That car is going 120 miles an hour?
Centimeters per
Oh.
second.
About a meter a second.
Okay.
Anyone have any further questions?
Can you figure out how many miles an hour it's going?
Oh, a meter. That's English.
Yeah. You know what? Slower. No.
What? I'm having fun. Free Fall by Javier.
Acceleration due to gravity. And what I'm gonna do is I'm gonna shoot out of this pipe a BB. And can you take this closer? As soon as the BB goes out of this, let's say this.
Why?
Well, this kind of switch, is gonna interrupt the electricity through the wires, and it's gonna let the can drop from that electromagnet. This one right here stop. This is an electromagnet. Okay. And the electricity comes from this electric source. You take it. Over there. Okay. Those are the main parts.
What are you going to show us,
What-
Javier? Javier, when the BB comes out and the can is released, what are we going to learn from those two things traveling?
That both the electromagnet and the switch are connected, so as soon as the baby goes out of the pipe, the can is going to drop. So they're going to start, the gravity is going to act on them at the same moment. And I have this pipe aimed to the can. It's exactly to the can. So they're going to start falling at the same time, at the same acceleration, everything.
What should we expect when they hit the ground? Which one will hit first?
Both, they're going to meet somewhere in the path of the can going down.
So they should hit at the same time.
Yes, if I shoot the BB faster, they're going to meet higher. If I shoot it slower, they're going to meet lower. Okay? So now you can go there.
All right, then what we...
I'm going to blow this out, the pipe. I'm going to blow the BB out of the pipe.
You are? Okay. by Cindy Odom and friends. Average.
That for every action there is an equal and opposite reaction. Because of this law, this ball will bounce off the wall instead of sticking to it or going through it. Fine.
Ready, stop?
Yep. Jesus.
This chair because the chair is pushing back on him with the same force as he's pushing on the chair. Then I need Brian to throw the ball.
I'll throw it to Dave Matt. Throw it to Dave.
However, differences in mass have an effect on action and reaction. When Brian throws this ball to David, Brian will not slide backwards because he has a much larger mass than the ball. The greater mass will have a smaller acceleration, whereas the smaller mass will have a greater acceleration.
Throw the ball. Dave. Nice catch. I'll beat Dave.
Keep on doing it.
He's on a roll. 3 times.
Curveball, Dave.
Oh my God,
Figuring Force by Amy Harrington.
The definition for force is energy expended when the speed of something is increased or when something is moved against the influence of an opposing force measured in joules. 2 things enter into every case where work is done. 1, the exertion of force, and 2, the moment of something by that force. Now I will demonstrate 3 examples of force with my lovely assistant,
Thank you.
Chris Green. Now, he will lift 3 books which weigh 25 kilograms to the distance of 80 meters. Chris? Very good. This is showing that showing the work relationship. Okay. Over here we have him. He is going to use a hammer now, showing work done while driving the nail in. Chris? Very good. Very good. Then, third example here, we have a bowstring, where he will be pulling back on the bowstring, showing himself doing work on the string. Very good. Then over here, we have the formula for work. Work equals force times distance. And this is the formula that you use when trying to work or trying to find work. And that's all.
Rotational Inertia by Kim Carmen.
Rotational inertia is the resistance of an object to changes in its rotational state of motion. Rotational inertia depends on the mass of an object and the distribution of the mass. The purpose of this experiment is to observe how objects of various shapes and masses roll down an incline and how their rotational inertias affect their rate of rotation.
That was beautiful.
Somebody's going to have to get down there.
Yep.
Okay, here we have 2 balls, both the same diameter, but the green one has the much larger mass. And Kristen will predict which one she thinks is going to get down there first.
the green one.
Okay. 1, 2. Green one?
Yeah.
Okay. That's how it's the yellow one. That's how it's the yellow one. Start one.
Sorry, but
Put it at the same time and in the same place.
which one?
The yellow one? Let's try it one more time.
You don't get nervous. Same time.
Ready?
Mm-hmm.
Yellow. The one with the lighter mass is the one from one. Okay, now let's do ones with different diameters but the same mass. which one will get there first. Okay. Okay.
Like a stick,
Yeah, which one do you think?
big one.
Big one?
Yeah.
Okay. All right. No?
Oh, I was wrong.
Let's try it one more time. So we can tell by this experiment that the one with the less mass and the less diameter is the one who will have the less rotational inertia. Okay, now let's do... Now we're going to see with these two cylinders, we're going to be able to tell if a different shape has an effect. Both these have different mass and different diameter. And how are we going to do this one? Which one do you think will get there first, Kristen?
The wooden
One?
or plastic.
Give it one more try. Just stay. In this experiment with cylinders, the one with the greater mass and the less diameter is the one that has the less rotational inertia. And I think that's all we should do. We're going to try an experiment with two cans, both with the same diameter, one with nothing here in the middle and one with a solid wash bit in the middle. Which one do you think will get there?
And Campbell's chicken noodle soup.
I say the empty one.
Okay. Roughly even. Same. Let's try it one more time. Okay, ready? I fixed it. So, what was the first one?
It's been...
Yeah. Okay, wait, shut the camera off. We have one ball with all the mass right here in the middle, and the ping pong ball that has all the mass on the outside. Let's see which one will have the rotational inertia.
Gentlemen, start your engines.
One. You want to do it one more time?
Mm-hmm.
Let's do it one more time. Here, wait. One more time. You can prove that both with the cylinders and with the solid ball, that the one with the more mass in the middle had a greater acceleration, and the ones with the mass on the ends or closer to the edge of the object had the more rotational inertia. Okay, that's it.
The Egg Drop Momentum by Kim Kuyanga.
One, two, go! One, two, go!
Want to try it again?
No.
Okay. I'm the assistant over here. I'm supposed to take this out.
Can I see out? Is that broken, is it?
I don't know yet. It's not wet.
Ooh, I heard something crack.
It's in a little baggie. Can I take it from the bag?
No. Leave it back.
No, I want you to do it again like a couple times now since we don't survive.
And take off the
Eggs
top.
okay. All right, take the step out. All right, egg goes back in. Doink. Ta-da! All done. Follow me.
Now can I give a little bit more force so I make sure it breaks?
Thank you.
Splat! Okay.
Don't go yet. Don't go yet.
Increase the volume. Splat.
All right.
Everybody go splat.
You ready?
Mm-hmm.
Splat! Splat! Splat!
Would you like to see it broke and if it didn't know how to
Didn't
do it?
break, I'm really gonna cry.
Darn it.
They're broken?
Gooey egg! Da-da-da-da-da-da. Do-do-do-do-do. Now what would you like me to do with it? Close up.
Okay, now stop it. Hi.
Hello. Read it.
The first box, in the first box, the time of impact was extended to 0. And because of the time of impact was greater in the first one, there was less force on the egg. And that's it. Yay.
Lenses by Raoul.
Well, I'm going to try to explain the difference between the image of a light, well, yeah, through the two kind of lenses. This how do you call it? It's up there. This diverging lens, as you can see, is thicker on the edge and it's thinner on in the middle, in the center. And the other kind is, and the other one is converging lens, which is thicker on the middle and thinner on the edge. So it's kind of the opposite, both of them. And here, well, here we can see the image of the light through the converging lens, and the strings try to explain how the image changed from the real, changed from the ball to the screen.
Can I put that in front of it?
See? Okay, so that from the bottom of the, you can move, okay. You can move, okay. You can take this. From the bottom of the image here, it's going to the top of the lens, and then it's gonna change to it's gonna go straight to the screen. Then the middle is just going through the lens straight, doesn't change, and the top one does the same as the bottom one. See? With this kind of lens, you can make a real, very, very clear image in the screen. And then now we have to watch the other kind of lens that makes another image. Now with this kind of lens, the diverging, you can't even put clear the image on the screen. See? You can't see the image of the ball here. Just spread out the light. And if we put the converging lens behind the diverging, it's gonna be neutral, or not gonna make any difference.
Hand them both to me. Now put them up together.
Wait, let me do this.
Te voy a seguir filmando yo. Yo aquí con pinche.
We're using here just a screen where I make a hole with form of a T. This is just paper and normal ball. The, what do you call this? Potato. The lens and the screen of paper. So that's it. Thank you, Sam.
That was good. Waves by Aranza Donet. Wonga, 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 wonga. Compliments of Mrs. Ahshead. Did you get that in the same one?
I'm Miss Ahshead and I'm gonna try to prove the wave. I'm gonna show it to you, okay? A wave is a wiggle in space and time. We have a transversal wave and longitudinal wave. The highest point in the wave is the crest, and the lowest one is the trough. And the distance to the crest, to the middle point, or the trough to the middle point is the amplitude, and from here to here is the wavelength.
The what?
Wavelength. Ready? You can get the frequency with frequency 1 over the period of time, or you can get the period 1 over the frequency, and you can get the velocity of the wave dividing 1 over to the frequency. Ready? Okay. Now, like this. Ready? This is
Wheel.
longitudinal wave.
You sure?
Yeah. Sure. Ready?
Wonga, 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 wonga.
You get that?
Keep on doing it.
And up, out, and in, okay?
All right.
In and out.
Ready? You see? Now, take the other one. You see how they're going up and down, up and down? Okay, ready? You see? They're going up and down.
Mechanical Advantage by Professor Brian Wagstaff.
Mechanical advantage, and this is my pulley system that I set up, and I'm lifting. What I'm going to do is I'm going to lift this mass 5 kilograms right here, 2 meters in the air, and I'm going to figure out different things about that. And the mechanical advantage here is 7. Okay, this is 1, 2, 3, 4, 5, 6, 7. This one doesn't count. This one doesn't count. Okay. First thing that I'm going to prove is that in order to lift this can 2 meters in the air, it's going to take 14 meters of strength, because you take mechanical advantage, which is 7, and you multiply it by the output distance, which is 2 meters. And that equals 14 meters. So when I lift this thing up 2 meters in the air, it's going to take 14 meters of string to feed down. Stand on the table and like hold the meter secure in the middle. Just look at me. Okay, what I did was I tied a string on here, a yellow string, to where I'm going to start pulling down. That way when we lift it up, this is where we can measure from. Okay, so I'm going to lift this thing 2 meters. Javier is going to measure it for me. I don't think it's going to work for 2 meters. 30 centimeters, 40, 50, 60, 70, 80, 90. Okay, 1 meter. Want to measure? 150, 160, 170, 180, 190, and that's it. Told you. 177. Okay, 177. Can you hold this around like this? I got no calculator. Okay. So instead of 2 meters, it's going to be 1.77. 1.77 times 7. Okay. That means that it's going to be 12.39 meters of string that we used. Okay, right now we're going to measure this. It's going to take a little time. Okay. This mark. Okay. This is 1 meter. Yeah. Two. Three. Four. 10. 11. 12. Point what? 30. 40. Let me see. Then 39. 9. So it worked out. Okay. So that did in fact work out. Be that. Okay. Okay. In this experiment, I'm lifting. To explain this more, I'm working against gravity. So I'm lifting 50. Since this is 5 kilograms, I'm lifting 50 newtons of force, and it takes me 7.717 newton of force to lift this thing, because you take your kilograms, which is 50 newtons, you take your newtons and you divide it by mechanical advantage, which is 7, and it comes out to be 7.142 newtons. So all it takes to lift this thing, out of my forces, it takes 7.17 newtons. Now, if I wasn't pulling this myself, and I wanted to balance this
system with a certain weight, so that it balances in the air, then you set it up like so. I take 5 kilograms, which is the weight that I have, and you divide that by the mechanical advantage, it comes out to be 0.714 kilograms. So it takes 714 thousandths of a kilogram, or 714 grams to balance the system. So if my calculations are right, then this right here, which is 714 kilograms, when I put this on this system, grams, excuse me. When I put this on, then those two supposedly should balance. I'm hoping this works. Is this thing renewable?
Yeah.
Yeah,
they're killed.
Hey, Brian.
Gee.
Brian, move the desk. Wait.
So you can see it.
Move the desk
Yeah.
totally.
Balance. 714 grams by mechanical advantage. And that is the way mechanical advantage works.
I like it.
I'm impressed. That worked out. Lasers in Reflection by Mason Cassidy.
Tell me how this looks, though, first of all. See that?
I guess.
I'm going to show and prove that the law of reflection is correct. The law of reflection says that the angle of incidence equals the angle of reflection. Okay. So I have a laser set up with a mirror and some protracted angles on a board here. I'm going to take some chalk dust, and we're going to be able to see that beam reflect out at equal angles off the mirror. And it does. Right in at 60, right out at 60. If you saw that, try it again. In 60, out 60. Do it with 70. And if I can get it, pretty much right on the money. And that'll be true all the way around. So that proves the law of reflection. That's it.
That's cool. Chalk dust. On the 70, I believe.
Right, out there on the 70, in right there on the 70. That's all there is to it. It's pretty simple. So that shows that the angle of incidence equals the angle of reflection, and those rays both come off at the same angle. That's it. All over.
I missed the whole thing.
What do you think, Stubb?
I couldn't see your face at all.
Ooh.
Center of Gravity by Christopher Breen. The center of gravity of an object is the point at the center of its weight distribution. The center of gravity does not have to be in a solid object. On the chair here, the center of gravity is right here in the middle, which is no material or mass. And here on this roll of tape, the center of gravity is right in the middle where there's nothing. But in other objects, like this tape, the center of gravity is in the middle of this tape. Another object which does not have any mass in its center of gravity is like a basketball. there's nothing in the middle, but that's the center of gravity. Alright. Upright if the center of gravity is above the area of support, which is the base. And here I will show you how the center of gravity is supported here. You keep on going like this until it shows that there is no support underneath, that there's no base underneath the center of gravity, which would be like right there, and then the thing would top on, like that. And that shows you how you need a base for something to stand up, the center of gravity. I mean, if you put this like this, all that underneath is a base, so that's why it stands up. And the table here, the center of gravity, is right here in the middle, and the distance between these four legs over here is the base, so that base supports this center of gravity. On the center of gravity of a cone, all you do is just go up 1/4 the height, which is right there, and that'll be your center of gravity. And here we have a little triangle. To find the center of gravity of a triangle, a geometric shape, you just go up 1/3 of it, and there's your center of gravity there. Welcome to Fun with Physics. Now I'm going to show you how to find the center of gravity by using a Plumb bob. If you notice, I made 3 little holes here. I'm going to put it on this knob here, then you put the tape here, and then you draw a line here. You have one line there, and you continue the process. And these two cross right here, and this third one, if I do this right, should cross in the same point, and that should be my center of gravity. You check here, it crossed right at the same point, and using the Plumb bob, I've proven that right here is your center of gravity. And that's one way to find the center of gravity. Let's see it.
Not the ball. Go.
Fun with physics! The center of gravity is the same thing as the center of mass, but in outer space, an object has no center of gravity because there is no gravity in space. The center of mass on a guitar is not in the middle, it's over here, right around here, because there's average mass on each side. And in a ball, it's just in the middle. And if I threw a ball just like this, it'd make a straight line. And if I threw this, the center of gravity would make a straight line. I mean, it would wobble, like, it'd go crazy, but the center of gravity, that little dot, would make a straight, smooth line, just like the ball did, the center of gravity of the ball. But it looked like it was wobbling, but it really wasn't. Thank you. Hello, welcome to Physics is Fun. Today I'm going to show you how to find the center of gravity of a meter stick. Put 2 fingers on each end of a ruler, then you keep on pushing in, and they will always meet at the center of gravity, which is the middle. Thank you. Now we're gonna show another one. A person can bend over and touch their toes, because their center of gravity is always below their feet, which is the base. But if you put the feet against a wall, try to bend over, you can't touch your toes because your center of gravity moves in front of your base, so the center of gravity has no base to support it, so it doesn't work.
Circle.
Energies by Sarah Darling.
Action.
Today we're going to study energy. The first kind of energy we're going to study is potential energy, which we symbolize with PE. This is energy that's stored and held in readiness. Some examples of this are a bow drawn, a compressed spring, or a stretched rubber band. The second kind of energy we're studying is kinetic energy. This we symbolize with KE. This is energy of motion. The boulder here has potential energy, which is, it's stored, the energy is stored, it is ready to fall. Here it is falling and it has kinetic energy. The law of conservation of energy says that energy cannot be created or destroyed. It may be transferred from one form to another, but the total amount of energy never changes. For instance, in a swinging pendulum, when the pendulum is up in the air, it has potential energy, but as it slowly moves down, it loses its potential energy and gains kinetic energy, but the amount of energy stays the same. And then it has kinetic energy when it's all the way straight down, and then it goes back up to potential energy and goes back again, and it keeps going on. We're gonna show you this with, Stubby's gonna do a demonstration on the swing. That's done.
The